While we're waiting, I'll just draw your attention to the breadth, again, of physics that's shown here, spanning astrophysics, high-energy theoretical physics, as Neil's earlier remark about string theory directed at Silvio implies, string theory in the past, biophysics, condensed matter physics. It's really a treat for us in the department to have a cross-section of leading young physicists working in all these different fields. And for this last talk, we're going to have a second-year Pappalardo fellow, Andrea Young, who did his undergraduate and graduate work at Columbia University. He also works in the area of experimental condensed matter physics, so we're really blessed by such a strong group in that area this year. And he'll be talking about Moiré superlattices and fractal butterflies, and certainly expanding our vocabulary. Welcome.
Right, so this title is in some way deliberately confusing. I promise by the end you'll understand at least what I was trying to convey. So I'm going to tell you about a very simple problem that has a kind of a complicated solution, and it'll echo something that Hugh said before, that condensed matter physicists get a lot of criticism for only measuring, or at least a good subset of condensed matter physicists get the criticism of only measuring the resistance of some material as a function of magnetic field. So you would think that it would be, a rather foundational problem to answer the question, what happens to an electron that moves under the simultaneous influence of a periodic potential and a magnetic field, right? Most crystals, most semiconductors, graphene, as I'll tell you about later, they all have a periodic potential. And if we're measuring the resistance of something as a function of magnetic field, well, this is surely the germane problem that we should solve. And at first blush, you'd think, well, okay, it shouldn't be too hard. After all, we can easily solve both of these problems separately, namely what happens to an electron moving in a magnetic field and what happens to an electron that moves in a periodic potential. So when you just have a magnetic field, it's a rather undergrad level problem to solve the energy spectrum of an electron, and it does the quantum mechanical analog of what a classical electron would do. It just spins in a circle, right? And this spinning is quantized into a series of discrete levels, and these are called Landau levels. And these Landau levels, they turn out to have a characteristic length scale that's associated with them, which essentially describes the size of these orbits. And not very creatively, this gets called the magnetic length. Now, if you just had a periodic potential, then it turns out that you can also solve this problem pretty easily. And the solutions are called block waves. And they look essentially like a plane wave, just like an electron propagating in free space, but they have an additional structure that has the periodicity of the crystal lattice. And so we'll just call that A. So in any crystal, there will be some periodicity. That's this crystal lattice. Now, of course, most physicists will know that when you have more than one parameter that you can change already, the problem is probably too complicated. But it'll turn out that this one is complicated in a rather special way. The crucial point is that let's say we take the ratio of these two quantities, so the magnetic length and the periodicity of this periodic potential. It turns out you can solve this quantum mechanics problem when this ratio is a rational number, but rather strangely, the number of solutions that you get is equal to the denominator of this number. Now, that's pretty weird, and it sort of is annoying to our physical intuition because, of course, as you sweep this parameter continuously, I mean, you can tune a magnetic field continuously, and in principle, you could tune the size of a lattice continuously. The number of solutions to your problem is going to fluctuate on any scale. No matter how small a change you make, there's always, you can find a rational number in between, and this number of solutions is gonna go crazy. But it turns out there's some, you can crunch this on a computer, and there's some method to the madness. And in particular, this is the solution that you get for a rather simple square lattice on a magnetic field. And so you can see that even though there's an infinitely fine-grained structure, I could zoom in on each of these, and I would always find more and more of these, more and more of this pattern. There is some order. In particular, there seem to be regions where these solutions are more dense, and then there are certainly large continuous regions where there are no solutions. Now, it turns out that this self-similarity and this infinitely fine-grained structure is exactly what that description of a fractal. It turns out this was This was actually discovered numerically 1 or 2 years before Mandelbrot coined the term, so it didn't get called a fractal at the beginning, but certainly the strangeness of this electronic spectrum was noticed right from the beginning. Now, so it got called the Hofstetter Butterfly, which you can sort of see that it looks like a butterfly if you kind of don't blink too quickly. And I don't know, I mean, it was also the 70s, so maybe there were some other aids to why it should be called a butterfly. There's a problem, though. I mean, it's a very beautiful spectrum. It's a very beautiful idea that this should be a generic property of crystals with a magnetic field, something that many condensed matter physicists study. The problem is that it's extremely hard to realize this. If you just take what's the spacing between 2 atoms in a crystal, and you calculate the necessary magnetic field to get to this regime, it turns out you need something like 10,000 Tesla. So unless you're going to do your experiments on the surface of a pulsar or a magnetar, which is going to present even bigger problems, this is very unlikely to be realizable. And the other thing which I'll address in a minute is, okay, this is a theorist's calculation. As experimentalists, what is the quantity that we would actually want to measure? So the person who discovered this, who did this calculation first, is actually quite famous. His name is Douglas Hofstetter, and in the original paper, he wrote the following sentence, which says that, you know, the idea, he sort of crunched these numbers, and he realized you would need thousands of Tesla, and this was much larger than what was available or was likely to be available just based on the type of materials that we as human beings have at our disposal out of which to make magnets. So he said the idea seems totally out of the range of possibility. He, in fact, left physics, maybe because of this, and he got a lot more famous. He won the Pulitzer Prize. He wrote Go to Lescher-Bach and so on. So, you know, maybe the fact that these fields are good was a boon to literature, but the problem sort of remained, let's say, unrealized and perhaps unrealizable, at least in the many years since. So before I tell you, you know, the punchline of this talk is going to be that, you know, now we can do it. But before I tell you that, I want to kind of make a slight digression on how we're actually going to tell that we've done it and what the experimental consequences of this would be. So, so what do we want to measure? Well, as Hugh mentioned, you know, we're going to measure the thing we always measure, which is the resistance as a function of magnetic field. Specifically, we'll measure the Hall resistance. And it turns out that actually the Hall resistance, if you calculate quantum mechanically, what you can get, you can, in certain situations, it turns out to be what's called a topological quantum number. So Dave Shea, I think, probably told you guys a few years ago about topological insulators. In a sense, the integer quantum Hall effect is the first topological insulator, and in a sense, one of the only real topological insulators in the sense that it only depends on topology. So what I mean by that is that if you calculate this Hall conductivity as a function of, say, magnetic field and the energy at which you've injected your electrons, you will find that it only depends on some topological property. And what that means is that if you deform your system a little bit, for example, you have a piece of semiconductor and you add a little bit of disorder, it doesn't actually change the topology. In the same way that if you have a donut and you just twist it a little bit, or you deform it just in a small way without making a new hole, it doesn't change the number of holes. And making a new hole is a rather violent process. So the experimental ramification of this is very straightforward. You measure this Hall resistance as a function of magnetic field in a two-dimensional material, and you find that in the right regime, you will get these very, very flat plateaus where you change, say, the magnetic field, and you don't find that the Hall resistance actually changes. Now, it turns out this is actually technologically useful. If you pick up a digital multimeter in your undergrad lab, at some point back in the process of calibration, it was actually calibrated to a quantum Hall sample, because it turns out this Hall resistance only depends on fundamental constants, and along with the Josephson effect provides the measurements of Planck's constant and the electrical charge of an electron. But the point is that, you know, you have a system where you may have some very complicated energy spectrum, and yet you have some physical property that is very directly related to something simple. It has to be 1 or 2 or 3, and it cannot be 1.01 or 1.2 or whatever. So what does this mean in our Hofstetter spectrum? It's actually, in some ways, really quite surprising that this should even matter, because, as I told you, in each of these energy bands, at any given value of, say, magnetic field, which is supposed to be this x-axis, you have a different number of energy states. But if I actually color, especially these empty spaces, by the expected Hall conductance, what I find is that each one of them is quantized. Now, that should be kind of surprising, because what I'm really telling you is that if I make an experimental system, and I put the experimental system at this range of parameters, and then I move it, let's say I'm filling up electrons up to this energy. So I'm filling up all of these bands, which have this infinitely fine-grained structure. I can move the magnetic field, for example, and I'm filling now a totally different configuration of bands with totally different microscopic structure, and I get exactly the same number. And not only do I get exactly the same number, it's quantized in units of some fundamental constants. So each of these bands, despite all this microscopic structure, has this topological invariant, which doesn't change as I change these parameters. Now, the problem is, OK, so maybe we understand that we should measure the thing that we always measure, and we should find that we should be able to see each of these gaps, and each of these colors should give us a different resistance, effectively, which should be quantized at a certain value. But again, we still have the problem that we don't know how to make the structure. We need a 10,000 Tesla magnet, and that ain't going to happen. So, so how we engineer the right lattice? So again, we have two options. The first is we can use a crystal lattice, for example, like graphene, but we have the problem that the fields that we can achieve are simply not big enough. Now, the other option would be to make an artificial lattice. So for example, you could pattern gates using nanolithography techniques and try to poke holes at some pitch, and let's say you have a couple of 100 nanometers that you might be able to pattern something. You might really push the technology like they do at Intel, and you might be able to get a little smaller than that, but actually that's not quite good enough, because it's very hard to make these perfectly periodic. They're going to be a little bit rough if you zoom in. And in any event, the length scales that you can conveniently do are actually now they're too big. So these are too small, and these are too big. So in this case, the field that you need is too small. In this case, it turns out that the field is too big. In this case, the magnetic field that you would need is too small to really be useful. But serendipity has it that there's another way. We'd really like to get a 10 nanometer superlattice, and we want it to be perfect. These are technologically very difficult problems, but luck can help. And the way we do this is to make one of these heterostructures with two layered materials. Specifically, we're going to take graphene, which conducts, but we're going to put it on top of boron nitride, which does not conduct. The important thing is that these have very similar crystal lattices. So they have the same structure, but they're not quite the same size. So when we do this, so let's sort of schematically do it. Here's a piece of graphene, and here's a piece of boron nitride. Now we're going to put the graphene on the boron nitride. And you can see that there's sort of all this interference. There's some places it's just kind of a mess, right? Because they're not exactly the same size. They're not exactly, well, in this case, the same color. But if we now, say, play with the twist angle between these two lattices, let's watch what happens, right? So what we see is that as we twist, especially when we align them, oh, you see that there's a long wavelength structure that emerges from the interference between these two slightly misaligned lattices, right? And especially at perfect rotational alignment. So if we put the crystals lined up one right on top of the other so that they're not mismatched, all we're sensitive to is the mismatch in their lattice constants, which is just small enough that we can make the perfect size superlattice to observe the Hofstetter butterfly. So it turns out this is exactly the same effect. If you have Moiré fabric, that's what it is. You have two lattices. They're not quite aligned. And so you end up with some superstructure which has a much longer wavelength than, say, the spacing between the fibers in Moiré silk, right? So that's the same idea here, except that now the lattices go in two directions, and that's why we get this two-dimensional structure. And it turns out, using graphene and boron nitride, you can make a Moiré pattern that has 14 nanometer wavelength, which brings you just to the perfect regime for the magnetic fields that we can, let's say, almost routinely access. And so this is a real thing. So here's a STM micrograph. So these are scanning tunneling micrographs taken by a group in Berkeley, but there was also work from MIT. And these are all the same size, but you can see these are different twist angles. So when you have a 20-degree twist angle, you don't see much Moiré. It's very misaligned. But as this twist angle gets smaller and smaller, this Moiré pattern develops in the graphene until you get something that's actually quite large. And so what we're going to do is take devices just like this, but we're going to measure the electrical resistance, and we're going to look for the signatures of the Hofstetter butterfly at very high magnetic fields, but not so high as I was telling you about before. Right, so the devices look like these header structures that he was telling you about, where we've piled these things on top and fabricated contacts so we can actually do these measurements. So before I tell you what happens when we do have a superlattice, we should just get acquainted with what happens when we don't have a superlattice. So I'm plotting magnetic field, and actually what we really change is density, but that's like changing the energy in the system. And these Landau levels, if you remember, they're just the electrons that move in a circle in magnetic field. So it doesn't really matter where you put an electron in, say, your sample. It's going to move in a circle, and it's going to have the same energy. So each of these lines is straight. The more magnetic field you put, the more electrons you can squeeze because the circles get smaller. And it turns out that if you just calculate what the Hall conductance is as you fill up these levels, you'll find that it just changes monotonically. And you fill up one of them, you have Hall conductance of 1. You fill up 2 of them, you have Hall conductance of 2, and so on and so forth. Now, if we measure some analogous quantity in our devices when we don't have this Moiré, in fact, we see that all these things, they just are lines. They go to the origin. And this is what's called a Landau fan. You can see why it's called a Landau fan. And that's kind of the normal thing that you expect without the superlattice. So what happens when we turn on the superlattice? So now we measure this in a device where we have this long wavelength Moiré pattern, right? Well, it turns out all of these Landau bands, they develop this fine structure, right? So I mean, this is a numerical calculation done by some of our collaborators, so it doesn't quite, I mean, their computer wasn't big enough, or they didn't run it for enough time to really get all the fine-grained structure, but you can see that this is certainly a lot more complicated than a single straight line, and if they had a bigger computer, they would never run out of complication to calculate. And so now if they calculate these kind of topological invariants, the thing that give us these quantized Hall conductances, they would find that instead of just going 2, 1, 0, 1, 2, it goes kind of crazy. So each of these gaps has a different Hall conductance, and it's oscillating as you go through it. And essentially, the cleaner our device, the more precisely we could do the measurement, we would see all this detailed structure. For now, we're just going to worry about whether we can do this at all. And so if we start with our Moiré-less graphene, and now we turn on this Moiré pattern, what we find is that, things get a lot more complicated. So what you're looking at now is, again, a sort of conductance as a function of magnetic field and a gate voltage, which is really tuning the density or energy of the carriers. And we're going to focus on this central region and all of these extra features. And particularly, you can see that there's this dark line in the middle. That's actually signifying 0 Hall conductance. But now it's joined by new dark lines that appear at a finite density, a finite energy. And there's other features that not every feature goes straight back to the origin. You can see that some of them interpolate not to the origin. They sort of crisscross each other. So if we make the comparison with our kind of theoretical calculation, what we can kind of quickly see is that, in fact, we're seeing these various features which trace just like these new gaps that are opening up in the fine structure of these levels due to this interplay between a periodic potential and a magnetic field. So in a sense, this is the first glimpse of this Hofstetter butterfly in a condensed matter system, where we've just used this superlattice to engineer the lattice to be the right size. Now, the sort of smoking gun, as I told you before, is the fact that this Hall conductance no longer just depends on the density. It bounces up and down. So if we look, for example, at a region where the field is low, you only see this 2, 1, 0, 1, 2. But now if we go to the regime where we have enough magnetic field that we're actually putting a quantum of magnetic field through each unit cell, we see that this thing goes totally crazy, but crazy in exactly the right way to tell us that, in fact, we have this Hofstetter butterfly. So let me conclude, I think, on time. So we've essentially managed to realize this thing. I mean, I'll be honest, this wasn't the experiment we were setting out to do. We were setting out to do a completely different experiment, but it was just luck that so happened. We ended up with a material that had this effect, and it kind of fell into our lap. So, I guess the message is you should do interesting experiments and then hope that you get lucky, but that's certainly the case in a lot of experimental physics. But now we have this system where we really have a great deal of control over its electronic structure, and we can play with a very rich electronic spectrum, and we can look at the effect of, what I didn't tell you anything about is the effect of electronic interactions. How do you reconcile the fact that all these electrons, they have a certain structure, they move with the superlattice, but they move also with each other? There's a lot of interesting things we can do. And more generally, it's another knob to turn in this idea of building heterostructures when you have these layered materials that have this rich atomic structure, like graphene or boron nitride and so on. The twist angle matters, and in fact, it's an engineering parameter that now we can play with to try and make new functionality, or at the very least, new toys for us to play with. So I'd like to thank in particular, my two collaborators. So this was a very collaborative effort between Pablo's group and Ray's group in the physics department, and in particular Javier and Ben, where we all work together on this. And of course, I think we should, on behalf of all the rest of the Pappalardo Fellows, I think we can give a last big thank you to Neil and Jane, who made all of this possible. So thanks a lot.
You know a little bit about Hofstetter. What is he doing now? What is Doug doing now?
I think he's still into consciousness and
But he hasn't had any major books since that one of about.
There was a book out a couple of years ago.
Yeah.
I don't think it made quite the splash of the first one. But,
as this one. Wow.
One can say a lot of wows about that talk, this talk and the others, but questions? Where did you get 43 Teslas?
Well, there's only one place you can get 43 Tesla. So there's a national lab in Tallahassee where they've pioneered making these fields bigger and bigger. But the problem is that I think the difficulty of making very high field magnets goes something like b squared or b cubed, depending on which part it is. So it's hard to make it. It's hard to make them any bigger, but they do a good job. But it's very impressive. So in condensed matter, we usually think of ourselves as doing tabletop experiments, but going to Tallahassee and using that magnet is the only time I really feel like I have some idea of what it's like to work on a particle physics experiment or something really big, large scale, because many stories tall and feels like big science.
Not quite on the surface of a neutron star, but
Not
close.
quite, yeah.
Close.
Well, that would be more expensive.
Yes.
Doing the same with an optical lattice?
Yeah, I think the problem is that the effective magnetic fields that you're able to induce in an optical lattice are probably rather small, but I don't know enough about what the engineering considerations are. I'm sure there's somebody in the audience who can answer this question. Maybe for all I know, it's already been done, but if it has, somebody should tell me, because we did cite it that we didn't know about it.
Yes, Aaron.
Would this help you make precision measurements of anything?
I think that as far as, probably no is the short answer. I can say no and leave it at that, but one never knows what will be needed.
The field has to be so strong.
In this case, the field has to be very strong, and there's much easier, if you want to measure, if you want to calibrate a multimeter, they already do that really well without using such big fields. In a sense, this gives you a direct view of the role of topology in the quantum Hall effect in a way that's not obvious in the same way from the normal integer quantum Hall effect. But I would say it's more of it's not particularly useful as far as metrology is concerned, because there are other things that you optimize when you try to optimize your metrology.
What were you looking for, if not this, and how did you recognize this?
Well, we were trying to make graphene essentially into a topological insulator, or at least to use the electronic structure of the lambda levels in graphene to make a quantum spin Hall effect. The reason we noticed it was that graphene, as Hugh told you, is usually a semi-metal. It has these Dirac cones, these linear dispersions that meet at a certain point. What really got us scratching our heads was that it turns out that in a related effect in these samples, actually graphene is a semiconductor. And this was highly unusual from our experience. And so it turns out this is all interrelated.
So you were focusing on the graphene, but what you found was that having it on this hexagonal boron nitride substrate basically gave you an entirely new phenomenon.
Basically what happens is that we've been studying graphene on boron nitride for quite a while. And when we first put it together, the hope was, we've removed impurities. It's just a perfect flat substrate. We don't have to think about its direct properties. That turns out to be mostly true until the crystals just happen to be perfectly aligned. Now, when we make these, we make them at a random angle. And it turns out there's kind of I don't know, a 1 in 30 chance or something of these effects really being strong. So it took us a while before we accumulated the statistics of very perfect devices, and we started to see that every so often something really different happens, and it turned out to be this as well as some other effects.
Wow, wonderful. Wow, that's a lot of patience in making all those samples.
At this point in time, is there a practical use of graphene in a product or a process?
So it is, there's several things under development. I think probably, I'm not totally up to date, but the thing closest to production on a major setting is for touchscreen electrodes. Samsung, the product was supposed to be out already, but I don't know that it actually is. My favorite thing that I heard, which I'm sure I've told this story to other people, is the idea of, so graphene is a transparent conductor. So there's this old problem in the design of automobiles of how to make a front windshield defogger. Nobody likes the air in their face, and nobody likes a little black line either. So there's a startup that I heard about that, that wants to make this front windshield defogger. One of those ideas that I wish I'd had. But I think that's about, there are many other things that are a bit far from applications, but the Europeans just gave $1 billion to find applications, so if they can't find it, then we're really out of luck.
On this touch-sensitive screen, is it measuring capacitance?
Yeah, it's using it as a capacitive electrode for a touch screen, that's right.
Wow, I'm very impressed by your questions, Neil. Anyone else want to match them? Yes, please.
Question, but are you going to write Douglas Hofstetter? I was looking him up while you were giving your talk, and just by the way, one of the books that he recently wrote was I Am a Strange Loop.
That's right, that's the recent one. Yeah. I Am a Strange Loop. It was the name of the last one.
The trouble with that book, of course, when we read it, and I read it when it first came out, I concluded it was either one of the greatest books of all time or an absolute piece of shit. I've still been unable to determine which side of the coin it lands.
Yeah, I won't comment on that because it's probably beyond my.
We'll be careful here to distinguish philosophy and literature from physics. Thank you very much. Great. Well, thank you so much, Andrea, for a wonderful talk. And let us give one final round of applause for all of the presentations, the speakers, the Pappalardo speakers, Janet Conrad, if she is still in the room, and certainly to Neil and Jane. Thank you all for coming.